This podcast is about VSEPR theory and how we can use it to figure out what the shapes of molecules are going to be. The basic principle behind VSEPR theory says that electrons are going to arrange themselves to get as far apart as possible. And this is because they're all negative and they want to be far away from each other because of repulsion. And the theory that we use is valence shell electron pair repulsion theory, which says that electrons want to be far apart. A group of electrons is either a bond, and it can be a single, a double, or a triple bond, it doesn't matter. Or a group of electrons is going to be a lone pair. So we think of a lone pair as a group separate all by itself. The shapes that we are going to learn are linear, bent, trigonal planar, trigonal pyramidal, and tetrahedral. These are the 5 that we have to know for this class. If you take other higher levels of chemistry, you'll learn other shapes beyond these. So 2 electron groups are the simplest, and what this means is that you've got a central atom with 2 bonds, and the central atom does not have any lone pairs. So it looks like this, and it's going to have a bond angle of 180 degrees because that's the farthest apart that the Y bonds can be. Examples are beryllium dichloride, which has single bonds, and beryllium, remember, can be electron deficient, less than an octet, and that's okay. It has a linear shape. And carbon dioxide, which also has 2 bonds, they're double bonds, but it doesn't matter what kind of bonds they are. The central atom carbon has 2 bonds, no lone pairs, and those 2 oxygens are going to be as far apart as possible, which again is going to be 180 degrees. So moving up, we have 3 electron groups, and 3 electron groups that are going to be as far as possible are going to look like this, like a triangle shape. And we can either have 3 bonds or 2 bonds and a lone pair. If it has 3 bonds, 3 atoms, then the bond angles are going to be 120 degrees because that geometrically is the farthest, the highest bond angles that we can get. Examples of this are BF3. Again, boron is a good example of trigonal planar because it's has no lone pairs on the boron, and it's flat, 120 degree angles. And then the other one is CH2O, where carbon has a double bond to oxygen and 2 single bonds to hydrogen. Again, it doesn't matter what kind of bonds. The central atom carbon has 3 bonds, and that's all that matters to make a geometry of 120, which is trigonal planar. The next possibility for 3 groups is 2 bonds plus 1 lone pair. And when that happens, the bond angle between the Y's here is a little bit less than 120. And that's because the lone pair takes up a little bit more space. It's a little bit fluffier. It's one way to think about it. It's less focused, so it pushes the angle a little bit closer together. An example of this is tin dichloride, which is SnCl2. The tin has a lone pair of electrons, so therefore its angle is going to be close to 120, a little bit less than 120 because the lone pair takes up space. 3 things as far apart as possible. So the names of these, in case you didn't get that, is trigonal planar, if it's 3 bonds spaced far apart. And then we call this shape bent because we name it by the shape of just the bonds. The lone pair is there, but the bonds are bent. It makes it like a little L sort of shape. So that's how we name the shape, bent. Okay, next up is 4 electron groups, and what happens with 4 is that you really have to start thinking in three-dimensional space here. 4 bonds as far apart make bond angles of 109 degrees. They're not flat, they're not 90. The angles get as big as they can, and 109 is bigger than 90. So examples of this, oh, and it's called tetrahedral. Examples include CH4. Carbon usually makes tetrahedral shapes. CH4, which has carbon in the middle with 4 hydrogens. This geometry, we try to show it with something that we call wedges and dashes. So this hydrogen here is coming out at us, out of the paper. And this hydrogen here with the dashed lines is going into the paper to try to show three-dimensional space. The other one is silicon tetrachloride. Again, same tetrahedral shape, bond angles are 109. The other option for 4 is 3 atoms plus 1 lone pair, and that looks like this. So it's got the X in the middle with 3 Ys and a lone pair. And again, these 4 groups are going to get as far apart as possible. And the bond angle here, instead of being 109, it's going to be a little bit less because the lone pair pushes it down a little bit. Examples, and it's called trigonal because it has 3 bonds, it's trigonal. And because it's like a pyramid, we call it trigonal pyramidal. Examples are NH3, nitrogen in the middle. Nitrogen has a lone pair. It's got 3 hydrogens here. The other example is PF3, phosphorus in the middle, 3 bonds to fluorine, and those are like a pyramid, and then phosphorus has a lone pair. And the bond angles, again, are just under 109. And again, why does this bond angle happen? Because a lone pair is a little bit bigger than a bond. It pushes it down just a little bit so that the bond angles are a little less than 109. The last way that we can put 4 electron groups is 2 atoms, 2 bonds, 2 atoms, and 2 lone pairs, and that looks like this. So central atom X has 2 bonds to 2 Ys, and it has 2 lone pairs. So again, because the lone pairs are bigger, it has 4 groups, so it's going to be 109. The lone pairs are going to make it a little bit smaller than 109, and because it, again, the bonds make an L shape, we call it bent. Examples include water, which you know probably from biology that it has a bent shape, but now you know why. And then sulfur dichloride, because sulfur has the lone pairs, it's going to have a bent shape. So the most important thing for shape is to make sure that you're drawing the correct Lewis structure, because you have to figure out if the central atom has lone pairs or not. So other molecular shapes, we are only going to go to 4, but they definitely go past 4. If you've got 5 electron groups, you can have shapes called trigonal bipyramidal, which look like this, seesaw, T-shape, substituting lone pairs for bonds. We're not going to need to know these, but you should be familiar. If it has 6 electron groups, then it makes what we call an octahedral arrangement, which is 6 bonds as far apart as possible. And these are the shapes that we get. So on the next page, I want you to stop your video and sit and work out the Lewis structures. That's the most important thing. Draw the structure first. Figure out where the lone pairs are, if the central atom has lone pairs. Use it to predict the bond angles and the shape. Name the shape. You don't have to draw it to scale, but you should label the angles on your molecule. And then when you're done, turn it back on and check your answers. Okay, check your answers when you're finished. I've labeled the bond angles, so check those too, and move on to the next problems. The last 6, again, stop and work out the problems on your own before checking. Okay, one thing I want to note is that when you have a molecule like CO3 minus polyatomic anion, this molecule has resonance structures. We can draw 3 resonance structures for this. You only have to draw one, and if you want to convince yourself you can do it, if you draw all of them, they are all going to have the same shape. It's one of the tests to make sure that you have resonance structures. They should all have the same geometry. And that's how to use VSEPR to figure out molecular shape.